Started?
Yeah, recording started.
Okay. So welcome back to lecture 26 on Riemannian symmetric space. Recall last time we defined something actually isotopic representation. So recall that if G acts on M smoothly, then you can uh, let G acts on smoothly and let P belong H is equal to let P belongs to M and H is equal to stabilizer of P inside G. Okay. Now H acts on TPM via isotopic representation. Topic representation. So tau from H2 TPM. Where this tau of H is really DLH. Actually, to define isotropic representation, you do not need this fact that G should act on M transitively. For that, actually, I have done little correction. Okay. So there actually I have removed this condition that G acts on M transitively because it was putting some unnecessary restriction. Okay. So now similarly, so what we have seen, suppose the action of G is transitive, suppose the action is transitive. So we have seen that this G invariant Riemannian structures on M are 1 corresponds to this H invariant in a product on TP. Okay, so that is the thing. Now, using this, we have shown that is dx square plus dy square by y square is the unique SL2R invariant Riemannian metric on this on upper half plane. So towards the end of the previous lecture, actually I have given you an exercise. So what is that? This exercise that using the above idea and without using Cauchy transform, Cayley transform, so that dx square plus dy square by 1 minus x square minus y square square is the unique SU11 invariant Riemannian metric on the open unit disk. So I have given you the exercise, but I have written down a sketch of the solution, so which you can read, and if there is any gap, you can fill up it. Okay, so this is easy. Okay, so now, so suppose here actually M is connected because Riemannian manifold has. So fact. So let M be a Riemannian manifold. With metric Riemannian metric. Metric Q. Then okay, by definition, then this Q is really IM invariant, right? Okay. This is a because this comes from straight away from the definition. Okay, so now okay, so we suppose okay, now we come back to our um, today's lecture. So this is much we have seen in the so then by definition Q is IM invariant. So okay, so what I recall also that I of Rn is equal to really what Mn. This is I of Sn minus 1 is On, and this thing, this I of Hn is really so not N1 distant union O minus cos N1. Suppose M is a Riemannian symmetric space, then Im equipped with a compact opponent topology is a Lie group. Compact opponent topology is a Lie group. Now you consider this ISN minus 1, which is On. So thus On equipped with a compact opponent topology is a Lie group. Is a Lie group. Now the thing is, so we are considering this example I of Sn minus 1 is equal to On. But the thing is, but On is also a Lie group. With usual matrix topology. So now, therefore, it is perfectly legitimate to ask this question that whether two topologies, that is compact opponent topology and this usual matrix topology, are same or different. Question. So is it true that the two topologies on ON, namely this compact opponent topology and matrix topology are same? The answer is okay to this question, yes. And similarly, you can ask this question for Mn or this I of Hn also, because this has some natural notion of topology there, and for those things also this two topologies coincide. So what I have done, I have really proved this result or written down the proof of this thing in my note, which I have forwarded to you. So you can read those things in, and I think okay. So this is my this is my proposition. So you can read those two things, this proposition, and you can ask me whether if you, in case you have any question or query. So now we come back to. So this is the thing. Now we actually we have seen that if the isotropy representation of a action, group action, is irreducible, then there exists a unique G invariant Riemannian metric on M. We have seen this thing. Let us see 2-3 examples of this example. So first example is your Hn. Suppose let M is equal to Hn. So what is G here? G is really Im naught, and Im naught is really SO naught N. Okay. So I will take this point En plus 1 as the base point. Therefore H is equal to, okay, that K is equal to this thing. Stabilizer of En plus 1 inside this G, and this is really what we have seen that this is really A001, so that A belongs to SON. Okay. And this is isomorphic to SON. Now if you look this thing Ten plus 1 Hn, actually we have also seen this. This is really this is the sign B0, so that B belongs to Rn, and this is linearly isomorphic to Rn, because actually this is also clear from this picture. If you really this is the picture of Hn. Okay. So now this is my En plus 1, and this is my tangent space at En plus 1. So, and we have also seen this. So Ten plus 1 is Hn. Now let G belongs to this G. Then this Lg, this is a map from Hn to Hn, given by this thing. Lg of M, so G dot M, and G is a linear map. So this is really G applied on M. Okay. Now since this Lg extends to a linear map, from this Rn plus 1 to Rn plus 1, so this implies D derivative of linear map is always itself. So dLgm is equal to Lg. Now the thing is, so consider the isotropy representation. Representation tau from this K, which is K is isomorphic to SON, to this orthogonal.
So G, dLgm is Lg or G.
What?
dLgm is equals to G or Lg?
This is Lg, but Lg is G.
Oh, okay.
Lg is equal to G.
Okay.
So this is where this is G. So this is G. Okay. Oh God, this is what. This is G. So this is orthogonal group of Ten plus 1 Hn. So this tau k is really what dlk En plus 1, but this is really k. Now what will be tau k applied on this tau element? Let us take any generic element of k. Sorry, this k belongs to k. This is small k, okay? So generic element will be 1, 0, 0, 1, and it will should act on a tangent vector. This is really V0, say. So this is This is A0, 0, 1. This B0. This is AB, 0. So therefore, isotropic representation is exactly the action of SON on Rn. Hence, the under suitable identification, isotropy representation is exactly the action of SON on Rn. And we have seen that the action of SON on Rn is irreducible. Hence, since action of SON on Rn is irreducible, therefore isotropic representation is irreducible. Hence, there exists a unique SO0 n, 1 invariant Riemannian metric on Hn. Now, as Hn up to scalar multiple. Now, as this SO0 n, 1, this is subset of IHN, and I have given you this. There is a fact in the beginning. I have told you a fact. So, what is that fact? Yeah. So then, if you take this M and suppose M is a Riemannian manifold with a matrix Q, then by definition Q is the IM invariant. Okay? And here actually the metric was dx1 square plus dx2 square plus dxn square minus dsn plus 1 square. Now this is the metric Q is equal to really dx1 square plus dx2 square plus dxn square minus dxn plus 1 square restricted to Hn is SO0 invariant. Hence, Q is the unique SO0 n, 1 invariant Riemannian metric on Hn up to scalar multiple. Okay. Now the thing is, I want to give another example per square. Let M is equal to really Sn minus 1. Here in this case, G is equal to I of Sn minus 1 naught. This is really SON. Then by exactly similar argument, to that of A, we see that the isotropy representation is irreducible. You can check it. Okay? So because that will be SON minus 1 stabilizer, and that's SON minus 1 will act on Rn minus. Isotropy representation is irreducible, and the metric dx1 square plus dx2 square plus dxn square restricted to Sn minus 1 is the unique this SON invariant Riemannian metric on SN minus 1. Similar conclusion is true for this thing that similar conclusion you can draw for that Rn minus 1. It's true for this image equal to R. Okay, so these are some interesting corollaries of this the fact that whenever this isotropic representation is reducible, and we will see later there are some other interesting corollaries also. Now this okay, so let us write down a proposition. So let pi m to n be a surjective submersion. These are smooth manifold. Okay, so m and n. What is this? What do you mean by submersion? That means if you look at this d pi p from okay, so d pi p from tpm to t pi p n. This is onto. This is the meaning of submersion. Okay, so this is the thing. So map f from n to p is smooth. If and only if this thing f composition pi from m to p is smooth. And this is for proof. You can see that any difference you can see genuinely. So this is the thing. Now this is the analog of this analog of a theorem which you have seen for quotient topology. For instance, there is a suppose quotient space. So x more x this is the quotient space. So this is the equivalence relation. And suppose M is a topological space. If from this quotient space to M is continuous, if and only if you compose this map, F composition pi is continuous. This is the analog of that result in the continuous category. So now I want to write an important theorem. So this is a very important theorem. So let G be a Lie group with Lie algebra of G is really G, and Lie algebra of H is equal to and H be a closed subgroup of G. With this Lie algebra of G, Lie algebra of H is equal to small h. Let pi from G to G mod H be the canonical projection. Given by this thing, pi G is GH. So let pi of E is really O, and what is this? Okay, let O is equal to pi of E, and pi of E is the H because this is the identity quotient. Then I look at this d pi E. So d pi will be a map from G to P naught of G mod H. This is a linear map, but it is a surjective map. Surjective linear map. Okay, with kernel of d pi e is equal to h. Okay, so with kernel of d pi e is h. And pi from G to G mod h is a surjective submersion. Now the thing is, so I have written this pi is from G to G mod h surjective submersion, so I can really apply this previous proposition. Hence, this f from G mod h to say n is smooth if and only if this f composition pi from G to n is smooth. So proof for the second part you can apply this previous proposition, but for the first part you can see as well. So this is the thing. You will use this thing in later. So let us see. So now we want to come doing some discussion, important discussion. The discussion. Okay, so let G, H is G, H be a Riemannian symmetric pair with this with okay, associated with a involution. With the involution sigma from G to G. So we have also in the, if this is a Riemannian symmetric pair, we have this. There are two conditions. We have this thing. This G sigma naught subset of H subset of G sigma, right? And this R G H is compact. There are two conditions. Now where G sigma is the fixed point of sigma, earlier you know. So this okay. So I am not writing that. So now let theta is equal to d sigma with the Cartan involution. Now you can write this k is equal to x belongs to G, so that theta x is equal to x, and p is equal to really x belongs to G, so that theta x is equal to minus x. Then this k is equal to this Lie algebra phase, we have seen that, and G is equal to k plus p, and this is the called Cartan decomposition. And okay, and this is direction, right? So the direction. Now by previous theorem, this previous theorem, so d pi e, this pi is the canonical position. Okay, pi is from G to G mod f. This canonical d pi e is a map from where. So this will be G to T naught G mod f is a linear surjective linear map. Is a linear onto map with kernel of d pi e is really, this is really Lie algebra page, and this is k. Now closely look, this k, g is equal to k plus p. So since this is linear and kernel of d pi is equal to k, therefore, so thus d pi e, this from p to p naught g mod s is a linear isomorphism. Okay. Hence, we can identify p naught g mod h with p via the isomorphism via d pi e, via d pi e. So you can identify p with d pi e. Now, so there is isotropy representation acts on T naught G mod S, and I want to see how that action transforms on P. So let us see that. So let X belongs to P. This implies so this implies d pi e. Okay. So d pi e x belongs to T naught G by S. So I told you that if f from m to n is a smooth map, so dfp is v is really d by dt of t is equal to 0 f composition gamma t. Okay, where gamma is a curve in m, so gamma is a curve in m with gamma 0 is equal to really p and gamma prime 0 is equal to v. I will use this fact repeatedly. So this d pi, therefore this implies d pi ex, this is equal to d by dt, t is equal to 0. This is pi of exponential of tx. Because exponential tx is a curve in the Lie group G with value at 0 is identity, and its derivative at the point 0 is x. Okay. So this is the thing. So that means this pi of exponential of tx is a curve in G mod s, so that its derivative at the point 0 or tangent vector at the point 0 is d pi ex, and at the point 0 it takes value o. Okay. Because so now I want to really find what is dl. Okay, so let h belongs to h, so this dlh, okay, o, this o is pi of e. Okay, o is pi of e, and this is really h. So dlh, so d pi e x. So this is really d by dt of t is equal to 0. So LH, okay, of pi of exponential of t. So I am applying this same fact again. So this is really d by dt, t is equal to 0. This LH, this is exponential of tx into h. So this is really d by dt, t is equal to 0, h exponential of tx into h. Now this I can write like this, d by dt, t is equal to 0, h exponential of tx, h inverse. Because h inverse belongs to h, I can write this thing like this. So now you can write this d by dt, t is equal to 0. What is this h of exponential of tx, h inverse? This is really exponential of g t r. Let us not write here. Exponential of t r g h x h. Okay. Now what is this thing? So this thing is really what? RG. Oh God, I have it. So this is really okay. So d by dt of t is equal to 0. This is pi of exponential of t RG h x. So now this is really what is the definition? This is actually d pi RG h x. So hence on P we get this thing. DL at 0 d pi e. This is equal to d pi e composition RGH. So here is the map. So this picture, this d pi e is a mapping from P to T naught G mod S, and this T naught G mod S, and this there is a map from here to here. So D LH naught, and this is really RGH. Okay. So this diagram is commutative, it says. Okay. Now the thing is d pi is an isomorphism. This is an isomorphism. So this is an isomorphism. So in the language of representation theory, you can say that isotropy representation is really equivalent to RGH representation of on P. Isotropy representation. So hence I am just writing this thing. Hence isotropy representation on tau. Okay, isotropy representation tau. Okay, on T naught G mod S is equivalent to RGH action on this. These two representations are equivalent, or you can say that d pi intertwines between two H actions. So what I am saying that H has an action on this P, and what is that action? Adjoint action, adjoint with RG action. Okay, RG via RG, and H has another action on T naught G mod S. Okay, by this isotropy representations. Okay, now by tau say, and there is a isomorphism. If you identify this these two vector spaces by d pi e, then these two actions are same. So that is the thing why I'm saying. Hence, okay. So hence we hello, are you able to hear me?
Yes, Munna.
Yeah, I can hear you.
Actually, there was a power cut. Okay, so you cannot see my screen, or see. Can you see my screen?
Yes.
Yes.
What I have written?
Yeah. Now we can see. Hence we get an.
Ah, Okay, so there is a power cut. So okay, so hence we get an. Actually, I am relying on my Geo mobile. Okay, so hence we get an 1-to-1. I get a 1-to-1 correspondence. Correlation between this set of all H invariant inner product on TPM and this RGH invariant inner product on inner products on P. So this is the invariant inner products on P. This is a 1-to-1 correspondence with H invariant inner products on TPM. Okay, so this thing is really, again, this we have seen that H invariant inner product on TPM that will corresponds to G invariant Riemannian metric on M. Sorry, TP in, I am writing TP in M, this T not G mod S. Sorry. Okay, sorry, hence we get one corresponding between H invariant and T not G mod S. Sorry, not this. And G invariant inner products on G invariant Riemannian structure on G mod S. So Mithanda, is it clear what I'm saying? Or
Yes, Mata. Yes.
Pushida, is it clear?
Yes, yes.
Acha, okay, so G invariant last time we have seen that G invariant structure on G. Now, so to produce a, that means they produce a G invariant Riemannian structure on G mod S. So it is sufficient to produce a RGH invariant inner products on P. And when this is possible? This is possible when this if this is certainly possible this when RGH is compact, and this there is a and so this is the second condition on RGH, the Riemannian symmetric pair. So there is, and this is the reason that we have taken this thing, the RGH is compact in the definition of Riemannian symmetric pair. So what I am saying that producing a G invariant Riemannian structure on G mod S, this is equivalent to producing an H invariant inner product on T not G mod S, and that is equivalent to produce an RGH invariant inner product on P. But since RGH is compact, so you can really produce a RGH invariant inner product on P. Therefore, you can produce a G invariant inner structure on G mod S. If you look other things which we have studied so far, actually we have not used this condition. RGH is compact. Okay? We have used the first condition to get the pattern decomposition, but second condition is really I am using now, and hence, so since oh god, where am I? Okay, since this RG H is compact, so there exists a RGH invariant in the program. Thus this G by H always possesses a G invariant inner product on it. G invariant Riemannian structure on it. And when this see, the thing is, when this isotropic representation is irreducible, so then you get a unique gene variant Riemannian metric. Now this boils down to the irreducibility of this RGH action on P. So, so this is the thing. So hence, okay, so okay, so now the right theorem. So let us write. So thus we have proved the following theorem. The following theorem. So let G comma X be a. Okay, so let us not write this theorem, this proposition. This is RSP and with Cartan decomposition G is equal to K plus P. Then d pi E is P to T naught G mod S is really okay. So pi with the projection map given by pi of G is G, and let O is equal to pi of E is equal to F. Then d pi E from P to T naught G mod S is a linear isomorphism. And this DLH not composition d pi E is equal to RGH composition d pi E on P where H belongs to H, and moreover there is a one correspondence between the following three sets. So this is really so G invariant Riemannian structure. Structures. Yes, there is. There any question? H invariant not products on T naught G bar, and this is really RGH invariant inner product on this yeah, and, and there is there are all moreover there always exists a invariant Riemann metric Q1. Now this is one. Now this is the thing actually. So thus we get that G mod S is a Riemannian manifold. We have obtained because there exists always G invariant Riemannian metric. So we want to show that this G mod H is really a symmetric space. So now discussion. This is the final. This will be the final theorem. So discussing that G B comma H be a Riemannian symmetric pair with associated with involution. The involution sigma. Okay. Now we want to show that this G mod H is Riemannian symmetric space. So we fix a G invariant. So Riemannian metric Q on G mod S. Okay, and which always exists. So which always exists. Okay. So this now we want to show that this G mod H is equal to Riemannian symmetric. Now since this metric is G invariant, since Q is G invariant, this implies LG belongs to isometric group of G mod S for every G belongs to G. That means this implies I of G mod S acts transitively on G mod S because left translations belong to the isometric group. Now we have seen that if some isometric group acts transitively on a manifold M, then to show something is a Riemannian symmetric space, it is sufficient to prove sufficient to produce geodesic inversion at a given point. Okay, so this was a result in page 311. So this is the result I am. Very good. Okay, so I hope you remember this thing. Okay, this is the result. So let M be a Riemannian polynomial so that IM is acts transitively on IM. That P belongs to M be so that there exists SP belongs to IM with SPP is equal to P and DSPP is equal to minus identity. Then we can show that M is a Riemannian symmetric. So when the isometric group acts transitively on a manifold M, Riemannian manifold M, then it is to show that it is a Riemannian symmetric space. It is really sufficient to produce a geodesic inversion at a given point. So to show this G mod H is a Riemannian symmetric space, it is in view of the position in page 311, it is this not sufficient to produce SO. Okay. This is where O is really pi of E. Now consider this following example. Consider the following example. So this suppose this example you take this thing. So let M be a RSS. M be a RSS. So this is my example. So G is equal to really, okay, let P belongs to M and G is equal to IM naught, and this H is equal to the stabilizer of H inside, so layer of G inside P. So we know that this M is isomorphic to G mod H. So G mod H is isomorphic to this M. And what is the isomorphism here? You take GH, that will really corresponds to this thing, that G dot P, right? And similarly O, which is really nothing but H. So, and that will corresponds to where? This will correspond to under this identification P. Okay. So now I want to produce SO here, and then let us see what it gives here in the M. Think this will correspond, since O correspond to P, this will correspond to SP. So here I want to want the action of SO on GH. So this is really the action of, this is on this GH corresponds to G dot P. That's what I am writing. SP of G dot P is simply, you can write SP composition G, SP of P. This is clear because SP fixes P. So SPG composition SP, this is really sigma G. So but I want to describe in this quotient picture. So this will correspond to where? So this will correspond to sigma G H. So hence this example. So this is my example. So, and this is a very concrete case. So hence the above examples suggest us to define this S naught G naught H. GS is really what? Sigma G of H. So this is my definition. Tapendo, is it clear?
Yes, Manoj.
So from Anway,
Yeah, I can. Yeah.
so we are using this concrete case to get an idea to how to define this SO. Okay. So hence this. So SO G not GH, but SO defines on this cosets. So you have to see that whether this is well defined or not. Now since okay, so since this H, okay, so now since H is contained inside G sigma, and G sigma is equal to G belongs to G, so that sigma G is equal to G. Therefore, S naught is well defined. Now I have to say that this I have to show that this S naught is the geodesic inversion at the point O. For geodesic inversion, we have to check three conditions. First condition, S naught is smooth. Second condition is SO naught is an isometric. And third thing is S naught is equal to 0 and DES not is equal to minus identity. These three conditional we want to show. Okay. Now as S naught GH is equal to sigma GH. Therefore S naught square GH, this is really, this is S naught GH, and this is really sigma S naught sigma GH, and this is really sigma square G H, because by definition, and this is sigma square is an involution, so sigma square is equal to sigma is an involution, sigma square is equal to identity. So hence this S zero square S naught square is all identity, and this S naught is equal to really S naught equals. Now we have to show that S naught is a smooth map. So S naught from G mod not H G by S to G by S is smooth. So if and only if. So I apply that lemma that since G to G mod H is projection, the pi composition is not. Okay. From G to G mod H is smooth. So by this previous theorem or something like that. So now, okay, so what is pi of S naught? Pi composition S naught of G. Really? Sorry, this is not pi composition. This is S naught composition. This is S naught composition pi of G. This is really S naught. Pi of G is really GS. So this is really S naught by definition sigma GH. And this is really what? Okay, this is really pi of sigma G, right? So that implies this S naught composition pi is equal to really pi composition sigma. This call this star. Now, okay, so this star. Now this, what is pi composition sigma? Now this pi composition sigma is the composition of two mass, smooth mass G to G sigma, and this G to G mod S. So this is really smooth, and this is smooth. Both are smooth. So is a smooth mass. Hence, so this will imply that S naught composition pi from G to G mod H is smooth. So this implies S naught from G mod H to G mod H is smooth. Now, as S naught is inverse is equal to S naught, this implies this. This implies okay. Therefore, this S naught is a diffeomorphism. It's a diffeomorphism of G mod H. So this is the thing we have got. Now, what is it is clear that S naught. Okay, so clearly this S naught is equal to really what? S naught of H, and this is really sigma E of H. This is H, and this is O. Hence, S naught is equal to 0. So now let Y belongs to P naught G mod H. So this implies Y is equal to something like d pi E x for some x belongs to P. So that means what is this? Okay, I have to find out what ds naught S naught Y, right? So this really, what is ds naught S naught? Y is really d pi x. So this is really ds naught composition d pi E x, and this is same thing as d of S naught composition pi at the point Ex. Now S naught composition pi is really by the star. This is pi composition sigma. So I write that. So this is really d of pi composition sigma E. So this is d pi E and d sigma x. So because d sigma E, you always write d sigma. Now this x belongs to P, so this is really this is minus of d pi. This is really minus of x. So d pi E, this thing is minus of. It's really minus of x, as x belongs to P. This is really minus of d pi Ex, and this d pi Ex is really y. So you do that. So this is minus of y. So hence ds naught not 0 is equal to minus identity on this t naught G mod S. Now we want to show that this is an isometry, and to show that this is an isometry, first observe that this thing. If you look at this thing, S0 composition LG applied on say MS. Okay. So this is really S0 LG of MS is really okay. This is composition. Okay. So S0 LG of MS is GMS, and GMS is really nothing but sigma of GMS, and sigma of GMS, sigma is in group homomorphism. So this is sigma G, sigma M H. Okay. That is really L of sigma G applied on sigma MH. But what is sigma MH? This is really L of sigma G. Sigma MH is really S0 MH. So this will imply this S0 composition LG. This is really L of sigma G composition SC. Okay. So hence we get this thing. S0 composition LG is equal to L of sigma G composition SC. Now this thing is S0 as an involution, so you can multiply S0 in both sides. So that will give you, this is equivalent to the condition S0 composition LC composition S0 is really L of sigma G. Okay. Now I have to show that this S0 is an isometry. That is the thing, main thing. So claim this S0 is an isometry. So let this MS belongs to this G mod S. And what is MS? This is really M dot 0. Okay. This M belongs to G. M dot O. So this and this U comma V belongs to T of M dot O G mod S. So let us see Q of S naught MS. So D S naught S naught D S naught S naught D S naught MS U. So T S naught MS. So what is Q of S naught MS? This is really Q of this is sigma MH. Right? So this is really D S naught MS U, D S naught MHP. So now you use the G invariance of Q. So Q, this is really L of sigma M inverse applied on sigma M H. Because of this matrix is G invariant, I am using that. So DL sigma M inverse. So D S naught MS U, and this is really where DS naught MS. This is really sigma MS. Okay. So this is my point, and this is DL sigma M inverse. So DS naught MS B. Okay. Now if you apply this L of sigma M inverse, sigma M H, this is really Q of H, and this is D of L sigma M inverse composition S naught. Okay. At the point MS. Okay. So U. Similar D of L sigma M inverse composition is 0 MS B. Okay, so now H is equal to your O. I can write O. Now I have a relation there in the previous case. This I will use this double star. See, this is double star. So if you will use this thing, this in place of G there will be a G inverse over there. So that will be S0 composition LM inverse. So Q so D is S0 composition LM inverse. So this factor I am writing like this. So now MS this MS is really M dot O. So I am writing this M dot O. Q. This is similar D of S0 composition LM inverse is M dot O B. So now, so Q of S, okay. So D of S naught, D, so I can use the thing, DLM inverse. This is M dot O, and this is really O, Q. Okay, so D is not, DLM inverse, M dot O, B. Now this factor DLM inverse M dot OU, this belongs to really T naught of G mod S, and this belongs to T naught of G mod S, and on T naught of G mod S, this is identity. DS naught is equal to identity, so this will give you. So this will be Q naught minus of, since this is sorry on T naught G mod S, this is minus identity. DS naught or not. Okay, so this we have proved that. So that will give you Q naught. So this is really this Q naught, this minus of so D LM inverse M dot O U. So minus of D LM inverse M dot O P. So this since so that will be same thing as Q naught D LM inverse M dot O U. So D LM inverse M dot O B. Now since this is a G invariance, this Riemannian matrix is G invariant. This will be Q of M dot O U. This is really Q of MH. Hence this S naught is a geodesic inversion. Now therefore G mod H is a Riemannian symmetric space. So this is a Riemannian symmetric space. And what is the isometry at other point? With this S G dot 0 is really, this is G S0 G inverse. Actually we have seen that. So this is the thing. So this we have proved. So Riju, is it clear? Or Riju is not clear? Pushtida, Mithunda.
Yes, Muna, this is
Yes.
okay. Yes.
Okay. So now let us write the theorem. Hence, this is the main theorem. Hence, we have proved the following theorem. And this theorem. So theorem. So let G, S be a RSP, Riemannian symmetric pair, associated with involution sigma from G to G. Let pi from G to G mod S be the canonical projection given by this thing, pi Z is equal to GS. Let O is equal to pi of E, lot O is equal to X is equal to pi of E. And then in any G invariant Riemannian structure. Riemannian Q on G mod X, and which is always exist. Which always exists. So G comma S becomes a Riemannian symmetric space, so that this S0 composition pi, okay, S0 of GS is really sigma GS. S0 composition pi. Actually, this is the same thing. Actually, so that it does not write this. So that S0 composition pi is equal to pi composition sigma, and this thing L of sigma G, L of sigma G is equal to S0 LG SC. Okay. So, in other words, the following diagram is computed. So this is the thing that G to G. This is map sigma. This is the projection pi. G mod F. There is a mapping here S0, and this is the projection pi. And this diagram is commutative, and this G by S to G by S. G by S, this LG, this is, so this is really what L0 composition LG. And this is really S0. This is S0 L sigma. So remark. So in the previous theorem, this S0 GS is equal to really sigma GS, and S of G dot 0 is equal to really S G dot S0 dot G inverse. This G dot means this is the group action. Okay, so yes, therefore so thus S0 is independent of S0 geodesic inversion. At O is independent of the choice of G invariant metric Q. So since this is S0 is independent of choice of the Riemannian metric Q, only it depends upon the involution. Therefore, consequently, SG also, consequently, any geodesic inversion, is also independent of the choice of geodesic inversion, right? The choice of Riemannian G invariant Riemannian metric. So this is an interesting fact that this geodesic inversion is independent of the Riemannian metric, but still, but if you think little bit, then it is a confusing fact. So how can this see the thing is geodesics are completely depend upon the Riemannian matrix. Okay? And the geodesic inversion or geodesic symmetry must depend upon therefore the Riemannian metric. And how is this possible? So let me give one question to think question. So let us think this question. I will answer this thing. That M be a smooth manifold with two Riemannian structure Q1 Q1 and Q2 on it. So that so Q1 is not a scalar multiple of Q2. But a scalar multiple of Q2. Suppose this M. Okay, so is it true that is it possible both MQ1 and MQ2 are Riemannian symmetric spaces? First, this is the question. Second question is that supposing your answer is yes, suppose you can show that this is possible. Supposing your answer is yes, is it possible? Is it possible that geodesic inversions are same? So you just think this question. This inversion. You just think this question a little. I will answer this question in coming lectures. But with this, I would like to stop. And if there is any question, I will be happy to answer it. By the way, if there is any question from previous lecture, also you can ask, or any doubt or query from previous lecture, also you can ask. Okay, so. Tapendra, is there any question? Pushtida? Rajesh Bhaiya? Stop the recording
Yes,
then.
Muna. Okay.
Stop the recording.
Munada,
Yes.
when you showed that the compact open topology is coincide with the topology on ON,